Okay, great. Welcome to this Google Hangout. The Google Hangout will be run by myself. I'm Dr. Leah Marks, and I'm a university teacher here at the University of Glasgow, and I'm one of the course leads. The other course leads, Sarah Meek, unfortunately can't be with us tonight. Hopefully we'll get to meet her in week 6 for the second Google Hangout.
Yeah, and I'm Dr. Kimia Huza, and I'm the deputy lead for the Cancer MOOC. So welcome, everyone.
So tonight what we're going to do is we're going to discuss quite a few of the questions that you've been asking. You've been asking some very good questions throughout the week and also in the previous weeks as well. But before we move on to doing that, we thought we would have a little look at some of the discussions that you've been taking part in this week. So there have been 3 discussions obviously this week, and we'll just give a sort of brief summary of some of the points that you've been making. So moving on to the first discussion, that was the one where we asked you to go away and to look at different types of cancer. So perhaps a cancer that you didn't know much about to begin with. And we asked you to go away and find some of the statistics about it and investigate just some facts about that cancer. We were very pleased with the investigations that you went away and did. It's been fascinating to just some reading around the subject of what you've looked at. I think between us we've probably looked at all the posts, and the variety of different types of cancers that you looked at I think was something that impressed me in particular. So you looked at things from very common cancers that probably some of us know quite a lot about to very rare cancers that possibly some people reading the post will not even have heard of. So I think the points that came out from that, one was that you're really starting to get a grip of the fact that cancer isn't just one disease. I think often people come at the topic of cancer thinking that it's one condition and it's under one heading and it's just all the same thing. But I think you're really starting to get a hang of the fact that cancer isn't just a single disease. Even within the same tissue or organ, there's a possibility that different cells would be affected, giving rise to different types of cancer. So I think that's something that certainly came out of this discussion. Some of the other things that came out of it were the fact that different cancers can have very different incidences. They may occur more often in one population or in another population. And the outlook for different cancers, the stage at which they're diagnosed, the prognosis, many things differ between cancers. And also even within the same types of cancers, there's different risk factors, different causes, and things like that. So I think you've got a grip of those kind of factors as well. Looking at how we treat and how we cure cancers, there was some nice investigation into some of these things, and again the aspects of the treatment for cancer and how different they are, and that carried on from weeks 1 and 2 in the discussions where you looked at how we might address looking at cures for cancer. And I think you've been talking amongst yourselves about the fact that one cure for cancer isn't a reality. In reality, what is likely is that more and more will become treating specific cancers with specific therapies. And I think the final thing that also came out of that discussion was the fact that the resources you used were quite different. So some of you will have used the Google tips that you've come across in week 1. Some of you may even have gone ahead to look at week 6. I think these searches, skills videos have been very popular and very well received. And some of you may have gone ahead and looked at the week 6 how to search PubMed video. But I know that a lot of you used very good resources for your analysis and for your investigations. So that's something that I hope you feel that you've improved on since you started the course and something that your skills have developed in. So overall, it's been a very good discussion, so keep the comments coming. If you've not taken part in this discussion yet, feel free to investigate. We'll be looking and keeping track of the comments that are made throughout the coming weeks.
Yeah. So I'll go on and summarise a bit the discussion you had about the environmental causes of cancer. And yeah, thanks again for taking part in that. There was a lot of comments and a lot of links, and that's really nice to see you sharing your sources with us. And talking of the links and your sources, I thought as well there's a lot of good critical appraisal of your sources, so you don't just go to any newspaper article and trust what it says. You've all been looking, researching, and that's been very good. there's one thing you've definitely all shown is that there are many known carcinogens or mutagens, but you seem to realize the importance of the dose and the frequency of exposure, so a high dose once or a small dose over a long period of time. That's quite an important aspect. And you've also realized the fact that cancer is multifactorial, so not just one cause gives you cancer, but it's an interaction between environmental factors and genetic predispositions, and that was give you a higher or lower risk. And you've also highlighted the fact that it's quite difficult to establish a causation of any environmental factor or agent, and that it can be quite difficult to tease the two apart because it is multifactorial. And finally, you've also raised the issue of public health. And once we know which lifestyle factors or environmental factors are possible causes for mutagen or carcinogens, who is responsible for keeping a good lifestyle? Is it the government's responsibility, or is it an individual responsibility to keep our lifestyles healthy? So that's been a very interesting discussion as well.
Okay, so moving on to the final discussion then of this week, we were looking at predictive testing and preventative, or you'll sometimes hear them called prophylactic measures that people might take in order to decrease the risk of developing a particular cancer that they're at high risk for. And we asked you to look at how you might feel if you were placed in that situation, if there were preventative measures that you felt that you would be willing to take in order to avoid a cancer, or if you really could ever put yourself in that position without actually being in the position itself in reality. And we asked you to weigh up whether you thought that predictive genetic testing for these predispositioning mutations to cancer, for example in the BRCA1 and BRCA2 genes, if predictive testing was a benefit or a curse. And there were many very interesting responses, some from people who'd never been in the situation themselves and some from people who had been in the situation. And it was very interesting to see what your views and your thoughts were. I've just pulled out some of the points when I've been reading through the discussion that have stood out for me. A lot of you said that you felt like you couldn't know until you were actually in the situation what you would do and how you would feel. And I think that's a very valid point to make. But something that I hadn't particularly thought about much before, but which quite a few of you brought out, was the fact that the predictive testing can be quite dependent on patient engagement, patient education, the resources available to a particular person. So not everybody necessarily within a population is in the same position to take advantage of the predictive testing offered. In the UK, obviously, this predictive testing is offered on the NHS, so therefore is freely available to anybody in the position to be tested. But a few of you made the point that not everybody will be aware of this testing, not everybody will feel able to go to their GP and ask for these types of tests if they have a history of cancer in their family. So I thought that was quite interesting. Many of you mentioned as well that it may depend on what situation in life you're in when you find out about the cancer. That may affect how you react to when you find out about the predisposition gene. So, for example, the age you were might make a difference. You might be willing to take more drastic preventative action when you're older or when you're younger. The support mechanisms that you have in place, so perhaps friends or family that you have that might be willing to support you through these decisions, could make a difference to what your decision is. And kind of tied up with that, a lot of you did emphasise that there would need to be genetic counselling and there would need to be some kind of support mechanism for you there in order to help you make that decision. I think another point that came out was the fact that for some people, having prophylactic or preventative surgery might make them feel that they were able to take some kind of control of a situation which otherwise they may feel they have very little control in, and that they were doing something positive, taking a positive step in order to help prevent this potential risk of cancer. But some others of you pointed out that even though you are taking control to an extent by having this preventative surgery, the risk of cancer isn't completely taken away. So, for example, for breast cancer, there will always still be some low residual risk because of the remaining breast cells that can't actually be taken away. So I think there was a lot of issues that came up during this discussion, which people discussed in a very sensitive and an appropriate way. So that was again a very worthwhile discussion. So I think we're going to start answering some of the questions and moving on. One thing I will point out at this point as well is that I know some of you have asked questions relating to perhaps your own situation, and obviously in this kind of forum we're not able to give out personal medical advice. So occasionally we put links to web pages which we feel people may find useful, but you should always consult your own GP, and they would be able to refer you to genetic counselling if that was appropriate for you. So we'll not answer specific medical questions for specific people, but we will look at some general points that may pertain to some of the questions that have been asked.
So there's no questions on the future run.
So yes, feel free to ask questions. We will just check the Twitter feed and check if there's any more questions that have come in.
We can maybe answer the most recent one first, which is makes the event more live, which is from Derek MacDonald, and it's about screening of other cancers. You can read the whole question. So there are a number of screening programs for some types of cancer, such as breast and cervical. Would it be worthwhile to increase the amount of regular screening programs to include the likes of basal-like cell carcinoma, malignant melanoma, testicular, rather than just rely on self-examination? So I think the answer for that is that yes, it would be beneficial, but unfortunately those screening programs don't exist because they don't fulfill all the criteria at the moment. So there are criteria that screening programs have to fulfill before they can be made general to everyone, and that's to make sure that the results from the screening tests themselves are accurate, sensitive, and also discriminatory, so that they don't give you false positives, that they would actually test or screen for a cancer that would be treatable, so that there would be a treatment or a reason and effect for actually doing the cancer, and cost considerations as well, so that there has to be economically viable. So if a screening program is too expensive in relation to the treatment expenditures, then that's whatever. Any others have I missed any?
That sounds like a good summary of the points. Okay.
We'll put some links as well to all our answers on the Future platform tomorrow, so that you can look at the answers in more detail.
Yeah. Just following on from that, the second question on the forum from Jenny Day reads that certain known hereditary cancers have been talked about, but what about other cancers? Is it because we have not yet discovered a hereditary basis for some of them, or is it that they're not likely to be hereditary anyway? Now this is a very interesting question, which kind of leads on to the pedigree diagram for this week, which we'll talk about in a wee minute. But before we do that, you will see that we've spoken mostly about inherited breast cancer in this week, and we've used that as an example because we know that breast cancer is a very common cancer in women, and it's one of the better understood inherited cancers. But I was having a little look, doing some research of my own this afternoon round about this question, and although we know that a lot of, well, a proportion of breast cancers, but only about 5% of breast cancers actually are inherited, and we know that certain colon cancers can be inherited as well, although again it's a very small proportion of them. There are actually other cancers that we do know that there's an inherited component, but either we don't know enough about the genes behind this inherited component, or we do know a bit about them but not enough to perhaps, or not enough people are affected to perhaps offer testing for them. So one of the cancers I looked briefly at was skin cancer, and so melanoma obviously is quite a well-known cancer, and in the UK about 12,000 people each year are diagnosed with this. But if you look at people who are diagnosed with skin cancer, about 1 in 10 of them will have some kind of family history of the cancer. And there is a gene, the CDKN2A gene, which is known to have mutations in this which can contribute to skin cancer. And people who have got a fault in this gene, about 1 in 4, 25% of them will actually go on to develop a skin cancer. So although skin cancer is one of these ones that we know there's a big environmental contribution to, and we'll come on to talk about that in a wee while, there is a genetic component, again, in a very small percentage of cases. Another one that I found quite interesting was pancreatic cancer. So only about between 2 and 3% of all cancers diagnosed are pancreatic cancer, and around 1 in 80 people will develop pancreatic cancer in their lifetime. But although it seems that around 10% of pancreatic cancers are, again, maybe due down to a gene fault of some description, researchers still haven't been able to pinpoint what this gene might be and what the fault is. And as such, we don't know as much about this as we do about perhaps the BRCA1 and the BRCA2 mutations. So yes, there are what we call possibly low penetrance genes that do affect other cancers. So it means that you're not as likely to get the cancer as if you carry a BRCA1 or a BRCA2 mutation, where your lifetime risk can be up to about 80% of getting cancer. For some of these other cancers, they're much lower penetrance, so you have an increased risk over the population, but not as big an increased risk. So I think that's possibly one of the reasons why you don't hear so much about the inherited factor. But certainly a lot of cancers do have hereditary factors, but they're not particularly well known, and they're not as often as big contributors as some of the well-known BRCA1, BRCA2 mutations. Yeah. We're going to have a look at the pedigree, or have you got any other questions? So this week you've been looking at the family tree of, let's call it up, a family who we're giving you some basic information about, and you might have thought there's not particularly much information there. It looks like a reasonably straightforward family, but there's actually quite a lot of features which we can see in this family which are quite important. Now, I'm going to just put the pedigree up so that you can see. I think I'll just get it on the screen actually. So, this, hopefully if you've drawn your pedigree, we'll put one up. Hopefully if you've drawn your pedigree, it will look something like the one that we've got here. Actually, could you possibly hold that while I thank you. So, what you should be able to see is we've got this lady here in the first generation. You can see we've got 4 generations, one numbered 1, 2, 3, and 4, and then we've numbered the people from left to right, 1, 2, etc. So there was a lady in the first generation who was affected by ovarian cancer, and she died in her 20s. So you can see that we've shaded her in because we know she was affected, and we've also put a diagonal line through her because we know that she has died. Coming down to the next generation, we have this lady called Betty Mackenzie, and it's important to note in that her breast cancer was bilateral, so that means it was on both sides. So these are 2 separate primary tumours. It's not one breast cancer that spreads to the other breast. These are likely to be 2 separate tumours, and that's a very important indicator that something may be going on with regards to an inherited cancer in this family. She was diagnosed at 38 and she died at 43, so we've included that information on her pedigree as well, because again, that's important information. You can see I've got square brackets around her, and this indicates that she has been adopted. It can be an important thing to include in a pedigree so that we know that we're looking at the actual correct flow of genetic information within a family tree. Moving down to the 3rd generation, you can see as well that we have these 2 ladies, Susan Mackay, who's 38, and we've marked her with a C because she's the consultant or the patient who's come to the clinic to ask for advice. We have a sister, Michelle, and she has an arrow pointing to her, and that's because she is the proband. So that's the person who brings the family to attention. So the person that the condition has been picked up in, and that's the reason that the consultant is at the clinic. And again, we've recorded the information about her cancer. If you go down to the final generation, we can see that there's the girl Lynn, who's 7 years old, and obviously she's not affected by cancer yet. So I think that's the most important features in the pedigree, and as I say, we'll put that up on the Future Learn site. So just a few things to pick out about that pedigree that, again, quite a lot of you picked out in the discussions, is that there are lots of generations that are affected. So it's showing what we call in genetics a vertical pattern of inheritance, and that's very common in cancers. Often in inherited cancer, often you will have people in several generations that are affected. We've also got a number of people affected with the same or with related cancers, and related cancers can be breast, ovarian, and potentially for a BRCA2 mutation you might see prostate cancer in a male in the family as well, and these tend to be hormonally driven cancers, so they are related types of cancers. In this family we only see women affected, but there is the possibility that in a family where there is a BRCA mutation, you may see an affected male with breast cancer. If a male has a BRCA mutation, he's got about a 6% lifetime risk of getting cancer. So you may or you may not see that. You also see that there's a lot of young people affected. Breast cancer traditionally we tend to see as a postmenopausal condition, although not exclusively. But in this family, we can see that people are affected in their 20s, 30s, 40s, so very young. And as I mentioned, we've got bilateral cancers as well. In this family, what you would probably want to do is you would want to test DNA from the sister. So you would want to test DNA from the affected person. We'll talk in a wee bit in a minute or two about some of the questions people have been asking about can we screen everybody for BRCA mutations. But before we do that, in this family, you really want to test the proband, because if we looked for a mutation in our consultant, well, we don't know if she's carrying a mutation or not, but we know that if there is a mutation in the family, her sister is likely to be carrying it, so she's a much better place, a much better bet to look for the mutation in. The child Lynn, who's only 7 years old, is too young to be tested, and generally you wouldn't offer testing to a child of this age. You wouldn't offer testing to the parents for a child of this age for an adult onset condition. Primarily because there's no risk-reducing strategies that you would use in a young child, and her risk of getting breast cancer before her 20s is very, very low. So you would effectively be taking away her right to make that decision for herself when she grows up if you tested her now. So the testing of young children for adult onset conditions generally isn't something that's practiced. One other point that some people have brought up in the discussion questions is that question of can cancer pass through an unaffected person? And the answer is, in short, that yes, it can. So you may have somebody in a family, you may have a grandmother who's affected, you may have an aunt who's affected, but perhaps the mother in the family isn't affected, and then maybe you've got a daughter who is affected. So in this case, it seems that the mother has the gene mutation, but she doesn't have the condition. And the reason for this is because, as we've already looked at, the penetrance of some of these mutations is between 40 and 80%. So there's still at least a 20% chance that somebody carrying a mutation might not actually get cancer. And that'll be down to a variety of things, partly chance, partly environmental factors. So it can pass through an unaffected person. It can also pass through an unaffected male, which again is something that people aren't necessarily aware of. So the BRCA1 and BRCA2 genes are on chromosomes 13 and 17. They're not on the sex chromosomes, so they can pass through a male who probably will be unaffected, and they could pass on to his daughters. So I think that's all I want to say about pedigree just now. So I think Camille may have another question that's come in.
Some more questions come in.
Great.
So one from Paul Wadley asking about telomerase as a cure to kill cancer cells. So I think that's actually been discussed already on one of the discussions. So you can have a look there for more information. But basically, yes, it is a good idea to try telomerase inhibitors. And they are being tested now. There is research being done, but none of them have gone as far as actually going into the clinic yet. But definitely an area to look at in the future. And we can maybe look at some more.
Quite a lot of comments.
Oh, we've got a lot of questions. Good. So should I answer maybe one that we've had on the Future Run platform earlier today?
Yeah, that'd be good.
So let's look at, for example, the electronic cigarettes, the new electronic cigarettes. This is something we've had to go away and look at, because when I was studying, they definitely weren't around. So the question was, are new electronic cigarettes, and it was a question from Stephen Allen, are new electronic cigarettes as healthy as the media proposed? Is nicotine on its own a carcinogen? And the short answer to that is it's too early to know. We don't know yet because the studies have not been able to be done yet. But it's definitely safer than tobacco cigarettes because they don't have tobacco in it or all the chemicals that normal cigarettes have. Normal cigarettes have about 7,000 compounds in them, nicotine being just one of them. So they are safer, but we don't know how safe yet. The compounds that are used are supposedly safe in foods, and that's how they've been tested, but their safety and inhalation is not yet known. And the other thing to mention here is that e-cigarettes are not actually, at least not in the UK, regulated yet to the extent of other nicotine replacement products such as nicotine patches and things like that. So the regulation is not in place yet either. For nicotine as a carcinogenic, yes, it is a carcinogen on its own, and these cigarettes do have nicotine in them. Nicotine can cause proliferation, angiogenesis, and migration of cells, and it can also decrease the effects of chemotherapy and radiotherapy in cancer patients. And the way it does that is by binding to nicotinic receptors, which are receptors on the surface of the cells, and that induces a whole signaling cascade and can affect cell behavior that way. So that's electronic cigarettes.
I've noticed that quite a few people have been commenting that the image has been on reverse on your screens, and that's quite interesting because we tried the initial image, which was this one. So I don't know if you can see the pedigree image. This was the initial image, which on our screen appeared in reverse. And this one initially appeared on our screen in reverse, but I see now when it's actually live, it doesn't appear in reverse. So what I was showing you was a mirror-generated image in the hope that that would appear correct on your screens, but this is what the real one should look like. So sorry about that. We'll not be posting. We'll not be posting a mirror image on your screens.
Yeah, the one we'll post on the Future Run platform
will be the real one. I wanted to do a written one rather than a pedigree software drawn one as well, because I noticed that on the comments a lot of people said they were drawing it by hand. So I've got another couple of questions here that people have been asking. So people have been asking about insurance and predictive testing results. Obviously predictive testing was something that we looked at this week. And people were asking, how does it affect your chances of getting insurance? Now that's a very interesting and topical point, and I think the answer in brief is that it's different in different countries. But I looked up the legislation in the UK, since that's where we're based, and essentially in the UK people should still be able to get substantial amounts of insurance whether or not they've had any predictive testing for a BRCA gene mutation. Now, obviously, with the whole field of cancer, it's hard to predict where it will go with in relation to predictive testing. It's very hard to guess where we'll be in 5 or 10 years' time. So the laws are put in place and the guidelines are put in place with a specific date for review. So there's a review this year of the current guidelines, and there's the actual guidelines run until 2017, when they'll be more formally and officially reviewed. But essentially, somebody cannot be asked to undergo a predictive genetic test or to disclose a family member's test in order to get insurance in the UK. And predictive testing after the policy has started also does not need to be disclosed to the insurer. Clearly, insurers do use family history information, so if you have a strong family history of cancer, then that will make insurance probably more expensive and harder to obtain. So the idea that there is cancer in a family will make the insurance probably more expensive, but positive predictive or favourable predictive test results, so if you've been tested for a BRCA mutation and you don't have it, then that can be used to offset the cancer risk that is in the family. So in some ways it actually works in the customer's favour. On the other hand, if you are actually affected already by the condition, then that can be used, and you've had a genetic test, that information can be used to, obviously increase the insurance. But overall, at the moment, people are quite well protected, certainly in the UK, and I think there's similar laws in the US as well relating to predictive testing and insurance. So I thought that was quite an interesting point that people had brought up.
Yep. I'll go for another question.
Yep.
So we've got a question, for example, on secondary cancer. So this is a question on the Future Learn discussion board from Karen Lindsay, and it's a question essentially about developing two different cancers many years apart, and whether this can be caused by radiotherapy or chemotherapy treatments applied to cure the first one. So yes, this is essentially a process called therapy-induced cancers of secondary cancers, although you have to be careful because secondary cancers can also mean metastatic cancers. So when you have a primary tumour, the metastatic tumours can be called secondary cancers as well. So, but here we're talking about therapy-induced cancers, and that is a known side effect of chemotherapies and radiotherapies, but in very rare cases. So only in about less than 1% of cancers are therapy-induced cancers, but it does happen. And I'm not going to tell you much more about it because we'll actually be looking at that next week in week 4. Yeah, that's it. Yeah, I won't say more.
Okay, I'm going to do something a wee bit different in terms of questions now, so I feel like I've been talking quite a lot about predictive testing. But there's another question asked which it said, what happens to the cell organelles during a mutation? Now, from Malakia, if I'm right in understanding the question, I think maybe you're asking what is the effect on the cell organelles of a mutation. Now, I thought I would move away from cancer to illustrate this one. So when the DNA is mutated, obviously nothing is particularly happening to the cell organelles at the time, to the other parts of the cell, but you've got your DNA is transcribed into RNA, which is then translated into protein, and the effect of a DNA mutation depends on where the protein that's made would be ending up in the cell. So the example that I wanted to use to illustrate that was from the cystic fibrosis transmembrane conductance regulator, or the CFTR gene for short, because it's a bit of a mouthful to say the full version. So this is a gene which is commonly found mutated in Caucasians, and in actual fact about 1 in 23 of the Caucasian population, or certainly the population in the west of Scotland, have a mutation, carry a mutation in this gene. And basically what happens is there's a mutation in the DNA that results in the protein having the wrong amino acid incorporated into it, or in some cases a missing amino acid altogether, and that means that that protein can't carry out its normal function. So the normal function of the CFTR protein would be to go to the cell membrane and to act as a channel for chloride ions and for sodium ions as well. So basically chloride ions go out the cell, sodium ions follow them out, and the channel functions normally. But if you have certain mutations in that, the channel either can't get to the membrane, or it doesn't fold correctly, or it can't fulfill its purpose as a channel properly. And therefore that means that the chloride ions can't get out of the cell in the normal way, and particularly in epithelial cells, such as ones that line the lungs and parts of the digestive tract, where this channel would be expressed, don't have a normal function because they're missing this protein. So that's how a mutation in the DNA would affect different parts, other parts of the cell. So I hope that answers what you were hoping that we would say.
Yeah. Okay, I've got another one here from Rebecca Little, and that's the question about how do doctors know if the cancer has stopped or if it has been removed completely? And that's going to be quite a short answer because essentially they don't. They can't be sure that it's been removed completely because when it gets very small, it can't be imaged anymore. And that's why it's very important for cancer patients to attend all their follow-up appointments because they're looking to see if it comes back. And if we're removing the cancer by surgery, you can look for something called margin-free resection. And again, I'm not going to explain that here because we're actually looking at that next week in week 4 in our surgery activity. But there is a way to see whether the surgery has taken out most of the tumor. And the other thing that can happen is that you can have micrometastases. So a primary tumor removed by surgery has actually already started spreading, but the metastases are so small that they can't be imaged. So from a scan point of view, it looks like they're not there. And again, we will talk about these next week in more detail, but they're essentially the reason why chemotherapy is often given to patients after surgery so that that can cure any micrometastases that might be there. And that's also another reason why doctors monitor the tumor throughout treatment to see that it is shrinking and responding to treatment, because if it is shrinking and it disappears, and they keep giving treatment for a little bit, then it's much more likely that it is gone. Yeah.
Okay. Yes, we've got quite a few more here actually. So somebody's asked, what is known about the relationship between obesity and cancer? I think that was one of the questions that came in just later on this afternoon. So we know that obesity is associated with increased risks of certain types of cancer, in particular things like breast cancer, endometrial cancer, but also perhaps less well-known cancers like the esophagus, the pancreas, kidney, thyroid, gallbladder. So there's quite a variety of cancers that you're more at risk of if you are obese. And there's been quite a few different mechanisms that have been suggested to sort of deal with this link. We know that fat tissue produces excess amounts of estrogen, and we know that high levels of that have been associated with some cancers like breast cancer and endometrial cancer. So that may in some part explain some of the increased risk, but also there's known to be an increased risk of insulin and insulin-like growth factor in people who are obese as well in the blood, and that may also promote the development of certain types of tumour. We also know that fat cells produce hormones, and some of these hormones may stimulate or inhibit cell growth. And if you look at the different levels, for example, of leptin, which is more prevalent or more abundant in obese people, then that seems to promote cellular proliferation. So there's also likely to be a variety of other factors that may be involved as well, but things that fat cells are producing may give rise to tumours. And if you are obese, you tend to have more sort of chronic low-level inflammation, and that's been associated with an increased cancer risk as well. So essentially, being obese is a risk factor for cancer through various mechanisms, which researchers are just getting to grips with what the mechanism behind these actually is. Okay.
Yeah, I've got a series of questions here. So these are from Donald Baines, and they were from the Futurama discussion as well. And the question is basically, is your check and repair enzyme identical for all gene transcription? And basically, no, it's not. So there's a variety of different repair mechanisms and repair enzymes in the cell, and that's because there's a lot of different types of DNA damage that can occur, and that each enzyme corrects a different type of damage rather than a different gene. And the examples of different DNA damage are single strand versus double strand damage, oxidative damage, alkylating damage, short patch versus long patch damage if it's just a short segment of DNA or a long segment. And this is all repaired by different enzymes that are very specific to the type of damage. And what's more, these enzymes often work as part of a complex, so it's not just one enzyme, but it's a whole group of proteins that work together to repair the damage. And you can also get mutations in not the repair enzymes, but the damage sensing proteins and mechanism. So that can also affect whether a cell repairs its DNA or not if it can't sense that there is damage. So basically, no, it's not all the same for all transcription, and there are a lot of different ways, and that's why there's not a magic bullet therapy at helping repair get on its way again. And the other point that brought up, which is quite interesting, is that for a cancer cell to develop, it actually needs a very specific amount of damage to its repair mechanism, because if a cancer cell completely wipes out its repair mechanism, it will start to accumulate mutations so quickly and accumulate so many that it will actually kill itself. And essentially, as we'll see next week, that's what a lot of the treatments do. So the cancer cell needs to have, to be able to become a cancer cell, needs to have a very specific amount of defect in its repair mechanism, not too much, but enough to accrue some mutations that will help. And there was a question too, which was, does this enzyme vary depending upon which gene it is checking or repairing? And again, they vary in each cell because each tissue expresses different sets of proteins and therefore different enzymes. And as I said before, it varies more specifically on the type of DNA damage rather than on the gene that it's trying to repair. And question 3 was why are there not more mutations then if there is a defective repair enzyme? And that again relates to the answer to the first question, because there's so many different repair mechanisms that can do the job that if one is defective, the others can still repair DNA to some extent. And yes, what's important as well is that you can still get mutations even if there is no damage to your repair mechanisms, because although they work very well, they are not 100% effective, which is how mutations happen in the first place. And these questions kind of lead on to, if I can answer another one.
Yeah,
another one by D. Jenkin, which was asking about why are BRCA1 and 2 associated with breast and ovarian cancer only if the mutation actually exists in the whole person. And that's because BRCA1 and 2 are DNA repair enzymes. And for this question, there's actually many hypotheses as to why that is. It is a very interesting question. And basically, because there are several repair enzymes, several repair mechanisms in the body, it could be that breast and ovarian tissues are just more susceptible or use more exclusively the BRCA1 and 2 pathways. It can be because these enzymes repair particular types of DNA damage that the breast and ovarian tissue are particularly susceptible to that type of damage. And there's other theories, for example, there's the loss of heterozygosity theory. So when a person inherits a BRCA1 or 2 mutation, this mutation is in only one of the alleles, and everyone has 2 copies of each gene. So in every person that has the mutation, they actually still have one normal copy of BRCA1 and 2. And that copy needs to be lost in a cell for it to become cancerous, which is why people who have the BRCA1 and 2 mutation don't get cancer everywhere. And so this theory basically says that in all the other tissues, when the cell loses the normal wild-type copy of BRCA1, that actually causes the death of the cell. But in breast and ovarian tissues, the signaling environments in those tissues actually means that the cell can survive losing the wild-type normal allele and then the cell can then go on and become cancerous because of the mutator value. So that would be one hypothesis. But essentially, there's a lot of hypotheses, and they are not all known. And I will put a link tomorrow to a paper that describes all the hypotheses on the platform.
Okay, I've got just two short questions here relating to headlines in newspapers. I think over sort of last couple of years. An interesting question that's just come in on Twitter. I think this is maybe our first Twitter question, or it's come in a wee while ago on Twitter, that says, does the size of the breast affect the chances of cancer? I.e., do smaller breasts have a lower chance of cancer due to less tissue being present? Now, if you have a look on Google, and if you Google breast size and cancer risk, very interesting what you find. You find lots and lots of newspaper headlines shouting that if you are a size D cup or whatever, you're more likely to have breast cancer. Now, this all comes from a study which doesn't actually quite say that. And I've just had a quick look. Certainly the NHS Choices webpage has quite a lot of interesting information about the study, and it says that the actual study itself, what they looked at was they looked at some genes associated with breast size and said that those genes were also associated with breast cancer, but they didn't say whether the genetic variants actually translated into higher rates of cancer amongst women who had larger breasts. Depends on cell type, I suppose, as well, because I would imagine that if you're looking at fat cells or whatever, you know, that you're not necessarily going to get the breast cancer developing here. So it seems that some of the headlines that have been around this subject need to be looked into in a bit more depth, and that might be an interesting thing that somebody could look at for the forum or discussion on risk factors associated with cancer. You could have a look in more detail at this scientific study. Obviously, we don't have time here to look at it in detail, but it looks like there might be more to it than the headlines that you'll have seen in lots of newspapers. There's also another interesting question, which I don't think we've dealt with yet, about heat generation.
No, we haven't.
So can you scan for tumours using heat due to the different way in which cancer's metabolism works? Somebody was asking if you can use, I think they were referring to a technique called thermography, where it's been suggested that as an alternative to say mammograms, that there could be the possibility of using heat scanners, and I know that's been something that's been in quite a few newspapers in the past year or two, suggesting this. I looked up some scientific papers on it, and apparently there was what's called a systematic review done in 2012. So a systematic review is just where someone goes and looks at lots of different studies that have been done and pulls all the data together and comes to a conclusion based on a much bigger sample size. And this was looking at heat scans, basically, to try and detect breast tumours. And what the study found was that there wasn't enough evidence to show that at the moment that thermography was a reliable enough way to detect breast tumours. Now, that doesn't mean to say that it can't detect some, or that in the future developments may be made that will improve its sensitivity, but I think you always have to be very careful with these new techniques in order to determine whether they are currently as good as the techniques that are in place already. So although heat scanning may be something that in the future could be something that's maybe used for different types of cancer, at the moment the scientific evidence does seem to be that it's not yet up to standard for a scientific diagnostic test.
Yeah.
Okay.
Yeah.
Get any more?
Get another question.
I've got another 2 or 3 as well.
Yeah,
we'll try and fit them all in. We've only got 10 minutes.
I'll answer them very quickly. So we've got another one from D. Jenkins, which is asking about cancer being a slow process. So he says that cancer is a slow process and often occurring decades after the cause. For example, smoking in the 20s, often cancer develops in the 50s, which is a big lag between the cause and the cancer actually occurring. So if that's the case, why does stopping the contraceptive pill actually reduce the risk of cancer straight away when you stop, and actually goes back down to normal by 10 years after stopping? So that's quite a difficult question and quite counterintuitive, because both statements are true. And the best way I can think of to explain this is to compare it to pregnancy-associated breast cancers. And before I scare anyone, pregnancy-associated breast cancers are very rare, so please don't be scared. But the risk of getting breast cancer is increased in the 5 years following pregnancy, but then decreases after that to a level actually below that, or that of women who have not had any pregnancies. So in the long term, pregnancy is actually protective, but in the 5 years straight after, the risk is actually increased. And that's effectively because there are different subtypes of breast cancer. So like we've said in the introduction, you've all understood by now that cancer is not one disease, and even one type of cancer, such as breast cancer, is not one disease, but it's made up of many different subtypes, and some are more aggressive and come on faster than others. And so basically, pregnancy increases the risk of maybe more aggressive cancers that come on faster, i.e. within 5 years following pregnancy, but that it actually has a protective effect on those that are less aggressive and that take much longer to come up, and that would come up in your 50s and 60s. And so that's why one factor, pregnancy in this case, or smoking or any other one, can actually have different effects on cancer risk, and why both statements in the question can be true, that cancer is a slow process, takes a long time, but that's stopping some risky activities can actually lower the risk quite quickly. And so that would be the same with smoking. And I also wanted to just say something as well before we scare everyone, that contraceptive pill, and not all of them, only some of them, can increase the risk of breast cancer, but they do decrease the risk of ovarian and endometrial cancer, which is cancer of the uterus. There is a link between the contraceptive pill and cervical cancer, but that could be due to women being on the pill being sexually active, and also being at high risk of having HPV, which causes the vast majority of cervical cancers. So I don't know if I should do another one. Or...
Yeah, try to. I've got another couple here. You do that one, I'll do that.
These last ones are short.
All right, okay, brilliant.
Because we don't have much time. So another one by Mariani. That's related because it's about breast and ovarian cancers. And she asks, can late menopause cause breast or ovarian cancer? And the answer to that is yes. So it has been shown that having a menopause after 55 can increase the risk of ovarian, breast, and uterine cancers. And the risk is also increased if menstruation starts early, that's between 12 years. And that's because if you're menstruating for longer, that means you have more proliferation cycles, more exposure to estrogen, and that increases your risk of breast and uterus cancer. And if you're menstruating for longer, that also means you get more ovulations, and that's why you have an increased risk of ovarian cancer. But yeah, not cervical, because that's mostly HPV again. So,
okay, yes, a couple of ones here. Ibrahim had asked, could you replace a faulty RB gene with a normal one from other animals? Now, an interesting point, other animals do have RB genes, but it would make a better therapy to replace the correct human sequence instead of the animal sequence. You'd actually be better just taking RB as would be found in a human and trying to replace that. And there's two sort of issues here. With sporadic cancers, you could use gene therapy to try and restore the tumour suppressor function, and there's currently trials going on for P53 from this point of view, and there's other ways as well that you could try and reactivate tumour suppressors within cells. But there's also the concept of germline, so that means inherited mutations, for example in RB. And in theory, you could potentially modify some of these mutated faulty genes, or you could screen for them. But with the issue of modifying the human germline, then comes all sorts of ethical issues. So there is potential there, and certainly restoring function for some tumour suppressor genes is being trialled. But when it comes to germline therapies, obviously there is ethical issues, and it can be a wee bit difficult. Another question that somebody had asked that I had written looked up an answer for was, yes, looking at the repair functions in mitochondrial DNA. So we know that most of our DNA is in our genome, in the nucleus, but there also is some DNA in our mitochondria. And in actual fact, the genes that are encoded by the mitochondria, there's much, much fewer of them. So while we've got about 3 billion bases in our nuclear DNA, we've only got about 16,000 in our mitochondrial DNA. But the mutation rate for this mitochondrial genome is actually quite high. I think it's said to be about 100 times higher than for nuclear DNA. And it was thought initially that DNA or mitochondria, the process of repair was non-existent, that there wasn't actually any repair mechanism. But actually, in recent years, it's been found that there are many pathways of DNA repair in the mitochondria, some of them the same as what happens in the nucleus, but others, they're found a unique pathway that has been found in mitochondria to repair DNA that isn't found in the nucleus. So in short, the answer is yes, there are seemingly quite complex DNA repair pathways within the mitochondria as well. A question somebody had just asked, I see on one of the mediums, I can't work out which one, was that is there any tissue or organ that does not get cancer? Which is quite an interesting question, and basically places where cells are dividing slower are much less likely to get cancer. So I think one of the examples that's given online is heart tissue. You don't see as many tumours, but you still do see them. So if anybody else wants to do a little bit of investigating about that one, that would be an interesting topic to look at. I've got one more question. I don't know if you've got any others.
Well, there's one that's
Was there one in? Okay.
And I had one more once before. I try and answer this one quickly.
Okay, you can answer that and then I'll answer mine quickly.
There's one that's just come in from Ioannis. And it is about the extracellular made to explain an important role in cancer progression and survival. Scientists managed to reprogram cancer cells back into their normal phenotype by altering their microenvironment. Is there any possibility for this to become a clinical treatment? And basically, I think what you're referring here, to here is of changing their phenotype from a differentiated phenotype to a de-differentiated phenotype, which is one of the things we'll look at next week when we're looking at grades of cancers. And basically, as far as I know, yes, there is definitely research going on to trying to redifferentiate or de-differentiate less tumors, and that could become a possibility. So yes, it's definitely being looked into.
One other question which people had asked was, how long does it take to get a predictive test result for a BRCA mutation, and why don't we just offer it to everybody? A few of you had mentioned that. Why can we not just screen everybody's BRCA genes to see if there's any mutation? In short, the answer is it can take a few weeks up to a month. It's not classified in general as a urgent test in the same way that, say, a prenatal diagnosis would be within a genetics department. And why we don't screen for everybody for BRCA, basically the BRCA genes are very, very big, and there's thousands and thousands of bases in them. I looked up how many there was about 80,000 bases in both the BRCA1 and BRCA2 genes. So if you can imagine looking through 160,000 letters to spot if one of these is mutated. And once you've found a mutation, which you probably will find some small changes in a lot of people, you have to then work out if those changes are actually pathogenic or just a harmless change. And basically you would get lots of false negatives, lots of false positives, and it would take far too much time to do it for everybody.
Basically, it comes back to what we said in the beginning.
Yes,
it doesn't
exactly.
fulfill all the criteria.
Yes, the criteria. Yeah.
For a successful screening program.
And so theoretically, the technology is there to do this type of screening, but the resources aren't particularly there, and you would have to argue, I suppose, whether or not it would actually be beneficial to do.
Yeah, we've got one last one from Judith Swan, who asks, can we detect alternative energy substrates to detect cancer? And that's referring to the fact that cancer uses different metabolic pathways to get its energy. So the answer to that is no, not yet, or at least not yet. Although other proteins can be used, and again, I'm referring you to next week. We'll look at biomarkers of cancer next week, and there are proteins and markers that we can use to determine if someone has a cancer or not. For the metabolism side of things, we can use the altered metabolism to image cancer cells. For example, their increased glucose uptake, because they take in more glucose due to their higher metabolism. We can put in a labeled glucose into the patient by injection, and then do a PET scan, and that means that any area that takes up glucose faster than the rest will light up, and that's how we can find tumors much more easily on the scan. So that's that one. So I don't know if there are any more.
Thanks. I don't think I've got any more
We're just
here.
about out of time anyway.
Yes, I think that's just about time. Thank you for all your contributions. I think that was the perfect amount of questions. I think there may be one or two that we've not managed to answer, but as I say, we will try and put some links later on onto the site, and also we'll do the same thing again in week 6. So hopefully, in week 6 we'll get a similar response, and you'll be asking even more in-depth questions. But it's been good. It's been enjoyable answering your questions and looking at all the things. So thank you very much.
Definitely, lots of interesting
That's
ones.
good. Yes, very good.
We hope you enjoy next week.
Yes, enjoy week 4.
Okay.
Bye bye.